Hi everybody, welcome to another video in Calculus 1, section 2.7, precise definitions of limits. So, at the beginning of this chapter, we define the limit of a function. So, let's go over that again. Suppose a function is defined for x near a, except possibly at a. So, what happens near it? If the function is arbitrarily close, meaning that it is as close as we like, for x sufficiently close, not equal to, and we write the limit of fx equal to a. So you get the idea. X get close to the point, then the y values get close to the point. But so actually that's what the definition is. So meaning that the values of the function can be made as close as to these values if we choose x close enough to 3, if x close enough to the values. So, of course, that definition, there's nothing wrong with it. The only thing that doesn't make it precise is it doesn't have any technical, or I should say any mathematical terms in it, right? Because when we said near and close, what does that really means? Right. So, remember, way back at the beginning of course algebra, we define absolute values is the distance from a point to 0, and so now we utilize absolute values to represent the distance. So what we say is the distance of f of x and L, this distance have to be close. I mean the distance between them have to be close, meaning that it's going to be, the distance between them is going to be small. And where x close to a, so this is also close. Also is a very small number. Right. So the way we write the definition is, we say f of x and L is as close as we like. So we can say the distance between them can be made less than a very small number, let's say epsilon. So we say for any epsilon positive, for any epsilon positive, we can make this, the distance between them, less than that point. So you can say let epsilon be 1, right? Then we can make the function and L as the distance between them less than 1, and said 1 is not enough, let's make it smaller. How about 0.1? Alright, in that case we still can choose f of x would be less than the distance between the function L would be still less than that number. So it doesn't matter what number you come up with, and that have to be positive. Doesn't matter what positive number you come up with, doesn't matter how small it is. We can choose, we can say the function and the limit can get even smaller than that. So it can get as close together as we want to for any values of epsilon. So mathematically, that's how it works. And we said as close as we like. If we want to establish a number, it can get even smaller than that. That's what I mean. Right. So for any epsilon like that, and it said if the function is close to L, as close as we want to, for every sufficiently close to a. So when we have epsilon, we can find delta such that this will be less than delta. So the idea is you have epsilon. You can pick any epsilon to be any small number. If you choose epsilon to be a very small number, I will give you a delta, usually a small number as well. In that case, if x, the distance between x and a, is less than delta, then the values of the function and L, the distance between them, is less than epsilon. Right. So let's look at this example. Let's first say, how about we let epsilon equal to 1. Let's say the limit equal to 1. So let epsilon be 1. What does that mean? Meaning that from the 5, the limit, I can go up 1 epsilon and go down 1 epsilon, meaning 1 up, 1 down, 1 up, 1 down. So the values is between 6 and 4. So I want the y values to be between 6 and 4. Now, in that case, we have to give a delta to guarantee this to work. Right. So if we look at these values and we say, if we can choose x values between 1 and 5, then certainly the y values is between 4 and 6. Or you can choose even smaller. I could choose, how about I only choose in that interval, within that interval, within this interval, y is completely between 4 and 6. Right? So that's the idea. If you say, give me some point that is close to the limit, tolerance, some epsilon about the limit, I can always find delta, so that with when the point is within delta away from x, the y values is completely within this. Right. Now, if we want to be smaller, how about we're going to let epsilon be 0.5 in this case. So from 5, we go 0.5 up, which is 5.5, and go 0.5 down, which is 4.5. And so the y values is going to be between this. In that case, I can choose the x values between 2 and 4 to guarantee that the y values is between 4.5 and 5. Right? So now you can choose, I can choose something like this interval. With that interval, the y values is completely between 4.5 and 5.5. So if this process can continue indefinitely, doesn't matter how small you choose epsilon, I can always give you the interval where the y values is completely within that interval. So meaning that it said the function can be made arbitrarily close to the values if we choose x sufficiently close enough to the point. So mathematically, that's how we write it. Right, so we say the distance between the function and the limit less than epsilon whenever the distance between x and the number less than delta. Right, so precise definition of limit is this. By the way, if this is the lecture class, my first question on test 1 is always write out the definition of limit. So you have to be able to write this out. However, this is online test. You cannot write the definition. You cannot write and pretty much anything on the test. So in that case, I'll spare you this question. But let's look at this. So we say the limit of the function as x approaching to a is L, written like this. If for any, so every little detail here is important. For any, that means arbitrarily or as close as we like to. So that's why we choose epsilon to be anything. So for any epsilon positive, there is a corresponding delta, meaning that we depends on epsilon we can find delta. So we can say delta is a function of epsilon if we want to, such that the value of the function is close to L whenever x is close to a. We write in this f of absolute value of f of x minus L less than epsilon whenever absolute value of x minus a less than delta. Right. Right. Let's look at this example before we actually do something. Write the proof for the limit. So in this section, we're not worried about how to find the limit. That we spend like 3-4 sections on that. On this section, we worry about how do we write the proof of the limit using epsilon and delta. So this is mathematical mathematically, how do we prove that the limit is such as whatever the number is? Right. Now, let the function be, look at the first example here. Let the function be x cubed minus 6x squared plus 12x minus 5, so that the limit equal to 3 by finding delta if epsilon is equal to 1. So, in this case, we draw the graph. So, the limit is equal to 3. So, we know the function can, from 3 can go something up and something down. And epsilon equal to 1, meaning that we can go 1 up and 1 down. So the y values will be between this. So in that case, we have to choose the corresponding x values to guarantee that the y values is within this. Then after we draw the line and the intersection to the graph, we see these 2 points. Then we say if x is between this interval, then y guaranteed to be in that interval. Right? Or if you're not sure about that, we can always make it smaller. How about we only look at this very small interval? When x is in this, y is on those interval. If we want to get smaller on the y interval, we can get smaller in the x interval. Doesn't matter how small you can get from the function to L, we always can find the x values that is close enough to A to make it happen. When x close enough to A, the y values will be in that interval. That's what I mean. So in this case, x can be in that interval around 2. So meaning that we go according to this on the graph, it will be 1 to the left and 1 to the right. So we can choose delta to be 1 or even smaller than that. So when epsilon equal to 1, we can choose delta to be 1 or any number less than that, or delta equal to 0.1, 0.5, or any number between 0 and 1. Or any number from 0 to 1. Right. So the idea is the epsilon is known, or the epsilon will be given, or we choose that to be arbitrary, and then we will find delta according to that. Right. Now let's look at the precise statement. The proof. So the step to write the proof is we start with the left hand side. We start with that. And then we will find delta in terms of epsilon. And then we write the proof in reverse. So the actual proof of the limit using epsilon delta is only half of this. However, to get to the function, we have to do the scratch work. So let's cut the page in half. Right now we will write the proof of the limit. Like I said, the limit will be extremely easy. Now, easy to find, but a little more difficult to prove. Like this one, if we find the limit when x go to 4, put 4 in there, limit easy. 4 times 4, 16 minus 15 is 1. So to find the limit is easy, but to prove it, it takes a little more work. Right, now, we start with this. So let's just follow that exactly. So we start with f of x minus L less than epsilon, and we end with x minus A less than delta. Right, so first when we look at the problem, we need to identify what is A, what is f of x, what is L. So if this is the problem, so f of x is 4x minus 15, A is 4, and L is 1. right? So we identify those things and then fill in this. So we start with a function for x minus 5 minus L1 less than epsilon, right? We write this, we have 4x minus 5 minus 15, sorry, 4x minus 15 minus 1, 15 minus 1 is 16. 4x minus 16, we can factor out 4, x minus 4. Now, we can, because 4 is positive, we can take it outside of the absolute values. And then we can solve for x minus 4 by dividing by 4 on both sides. Right, so we start from here and we end up with x minus a is 4, right? So we end up with that. And after that, we will make this 2 equal. So in that case, we're going to choose delta to be equal to epsilon over 4. Right, so this is just the scratch work, it's not the actual proof. Now, over here is actual proof. To the proof, when we write that, it's like the definition. It will have this. For any epsilon greater than 0, meaning that doesn't matter how close the function and the limit need to be. For any epsilon delta, epsilon less than positive, we can find delta equal to epsilon over 4. So on in that case, we just say for that we're going to choose delta to be equal to epsilon divided by 4, so that by the way, when we write f of x minus L less than epsilon whenever x minus a less than delta, we mean the equivalent to this is if x minus a less than delta, then f of x minus L less than epsilon. So when we write that whenever this happen, meaning if this happen, then we have that. So now we just write in reverse. So that if x minus 4 less than delta, which is equal to epsilon over 4, and we just write this in reverse. Then now we write in reverse. Yeah, multiply the 4 over and take the 4 inside, and we write that as 4x minus 16, and we write that as 4x minus 5. Keep doing that. And of course this is f of x. So pretty much I just write this in reverse. Because that is true, so we say limit x equal to 4 for x minus 15 equal to 1. Right. So if we actually need to prove, that's what we need. We do not need this left hand side. We need the left hand side so we can actually find out what do we choose for delta in terms of epsilon. Right, so simple enough. Right, next we do the same thing. Find the limit of this negative 2x plus 7 when x equal to 5. First of all, the limit is easy to find, right? Put in the numbers. That's pretty much it. So first, let's find the limit. So polynomial, I just put the values in it. Negative 10 plus 7 is negative 3. Right, so in this case we will say f of x is negative 2x plus 7. A is 5. And the limit is negative 3. Right. So we start with absolute value of f of x minus L less than epsilon. And we will end with x minus a less than delta, or of course if x minus a less than x minus a, meaning x minus 5 because a is 5. Right, so this is where we start with negative 2x plus 7 minus L less than epsilon. Right, remove the parentheses. Inside absolute values we have negative 2x, 7 minus negative 3, so 7 plus 3 plus 10. We can factor out negative 2. Give us x minus 5. Now, the negative 2 inside the absolute values, we cannot take it outside. But we can write negative 2, meaning we split the absolute values for negative 2 and for x minus 5. The result is still positive. So that's what we have. Absolute value of negative 2 is 2. So we have 2 and x minus 5 less than epsilon. And then of course we can divide by 2. So x minus 5 less than epsilon divided by 2. Now that's exactly the form we want. In this particular, we will let delta equal to epsilon divided by 2. Right. So now we have that, and our own home proof. That's all we need. By the way, even though the proof we only need this, but it would be nice. We just need to write everything here in reverse, and still work just fine. So the proof. So we start with for any epsilon greater than 0, we choose delta to be epsilon divided by 2. So that is the same thing as saying when we have epsilon, there is the corresponding delta. So if you give me epsilon, I will just divide by 2, and that will be the delta. So that if Now I write this x minus 5 less than delta, and delta is set to be equal to epsilon divided by 2. Then I just need to write everything in reverse, and that completes the proof. Multiply 2 delta epsilon. Right, because if you start the proof here and then you end up with this kind of not counterintuitive, but if you write this in reverse, I mean this process from top to bottom is intuitive. Write in reverse kind of not, because from here all of a sudden we introduce negative 2. That's kind of not very intuitive thing to do, but we know we have to do that because we just need to write this in reverse and take the negative 2 inside. Multiply it out. And we write this and here we see that this is f of x and this is L. So that means the limit when x goes to a, which is 5, the function equal to the limit. Right, so that's how we prove it. And then you say the function is too easy, right? We just have linear function. What happens if we don't have linear function? And what do we do? Right, I'm glad you asked. Now we have the function that is not linear. By the way, on this one, the proof, of course, we know. We just write backward. We start from something, we end up with something, and then we write everything in reverse. That will be it. Right, so same thing. And we start, first of all, let's just write the function is x squared minus 1. The values of x approaching 2, limit 3. Now so we once again we start with absolute values of f of x minus L less than epsilon, and then we end up with x minus a less than delta. This one a little bit different because we don't have a linear function. We have x squared. That makes things a little more interesting. Right, so let's start. X squared minus 1 minus L3 less than epsilon. So we have x squared minus 1 minus 3 is minus 4. Right, so that's good. But then how do we end up with, because like I said on this one, we're not going to write the proof. I mean, of course, we can still write the proof in reverse. But how do we end with? Because this problem is a little bit long, so we just going to write the scratch work. For the proof, you can just write everything in reverse, and that should be fine. So how do we supposed to end up with this? From there, right? Good thing is, by the way, a is 2, so we end up with x minus 2 less than delta. So we need to have x minus 2 in it. right? Then we say like x minus square minus 4, it can be factor, right? That's good. And then just like last time, we can split the absolute values. And if we want x minus 2, why don't we just divide that? Right. And then we say, why don't we make that equal to delta? And my answer will be, you cannot do that because here we have the x in it. Earlier delta only depends on epsilon. It cannot have x in it. So that's the big problem. Here we have to make some adjustment here. First of all, in that case, this will be a little difficult. So this trick is, let's say epsilon be 1, for example. And you say, why do we choose 1? Can we choose 2? And I say, yes, you can choose 2, 1/2, whatever the number is. So in this case, suppose it is 2. By the way, we're not going to choose epsilon again, but suppose it is 1, or 2, or 5, or 0.5. Any number will do. Any positive number will do. So suppose that, I mean, I'm not choosing epsilon to be 1. I'm choosing, suppose that x minus 2, suppose delta is equal to 1. Just bear with me for a moment. Now, if delta is equal to 1, what do we mean by that? If delta is equal to 1, meaning that x minus 2 less than 1, right? If x minus 2, absolute value of x minus 2 less than 1, meaning that 2 will go 1 to the left and 1 to the right. So add 1 is 3, subtract 1 is 1, meaning that x have to be between 1 and 3, right? If absolute of x minus 2 less than 1, so x is between So x is between 1 and 3. Right? If delta, suppose delta equal to 1, then x is between 1 and 3. Now, if x is between 1 and 3, you put 1 and 3 in here. Epsilon divided by x plus 2 if you put 1 and 3 in it, 1, what do we get? Epsilon divided by 3, right? Now if we put 3 in it, now let me ask you this, epsilon divided by 3 and epsilon divided by 5, which one is smaller? You should choose this one because the denominator is bigger, the quotient is smaller. So, this one is smaller than the 2. So in that case, we can kind of scratching this out. Now, what we choose delta is, we're going to choose delta to be whatever smaller between 1 and epsilon divided by 5. If that is the case, then that guarantees for this to happen, right? Because if delta equal to 1, so x minus 2 less than 1, which is good already. So that's perfectly. If it is not, if x minus 2 is not less than 1, in that case, you can choose delta to be equal to epsilon divided by 5. And that will work. So, how about this? So we have, if you give me epsilon, I will do two things. First, I take the minimum of 1 and epsilon divided by 5. Right. If it is less than 1, it's perfectly fine. Now, if it is not less than 1, then we can choose it is epsilon less than 5. In that case, x minus 2 will be less than epsilon divided by 5, which is perfectly fine. When we write in the reverse, it will work, because if x minus if delta is equal to epsilon divided by 5, we can say that it certainly would be less than that one is cannot really wedge in there, but this one will guarantee to be less than 5, and that of course is the minimum of all of the epsilon divided by x plus 2. Yeah, we certainly have that. So if x minus 2 less than 1, it is good. If it is not, yeah, pick it is less than epsilon divided by 5. In which case, it guaranteed to be less than that. And multiply both sides and write thing in reverse. It's going to work. It's going to work. Right. Then we say, if I don't want to choose 1, can we choose 2? And of course, can choose 2 as well. But like I said, the proof will be in reverse. I'm not going to write that because that takes too much space and time. The idea here is we can find delta in terms of epsilon. Right. Now, suppose we choose delta to be 2 instead. Right. So delta is 2, meaning that from 2 we can go 2 to the left and 2 to the right. So that means from 0 to 4. So if we have delta equal to 2, meaning x minus 2 less than 2, so x is between 0 and 4. Right, now we will check. Put 0 in epsilon divided by 0 plus 2. That gives us epsilon divided by 2. And if we put 4 into x, of course I'm going to put that 4 into here. And out of those two, this one is smaller, so ignore that. And I will say, in that case, I will choose delta to be the minimum of these values or these values. Because if it is less than 2, it already is less than 2. So it's good. If it's not, depends on epsilon, choose epsilon divided by 6, and we'll go with that. And that will guarantee, it will, what's that? It guarantee it will be less than epsilon divided by x plus 2, and then we can work in reverse and get back to the function, get back to this. Right. So that is where we have a square function. When we have the qubit function, things would get a little more complicated. But I don't think we get to that complicated. All right, so as the limit of the function, when x approaching to a number and the values, the limit is finite. Now what happens if we have infinite limit? Right, we can have similar thing. We say the limit as x go to a of the function equal to infinity means that this can get as big as we want to. So when it gets close to a, it will get extremely big. So that's why we do that. And now let's write the proof. So once again, we instead of given delta, instead of given epsilon, we go start with any positive number n. Doesn't matter how big it is, we can always find delta. And in that case, the function bigger than n when x minus a, absolute value of x minus a less than delta. So the proof of this, calculate the limit. We start with the scratch work, and then we write everything in reverse. So we start with this, f of x greater than n, and at the end we end with, by the way, in the limit, in the definition, in the definition of limit, you can instead of write x minus a less than delta, you can write x minus a less than delta and greater than 0. But greater than 0 is kind of redundant, because we know that absolute value is greater than or equal to 0, and we know that it's not equal to 0. So we just make it, it can be greater than 0 as well. But usually, I mean, you can just write like this. Right. So that's where we start, and then we end with x minus a less than delta. We don't need to write greater than 0, because it is greater than 0 already, being absolute values, and it cannot be equal to, because x doesn't have to be, x doesn't have to go to a, it just need to go close to it, as close as we want to. Right. Now we start with this. F of x is 1 over x minus 2 square, and n is n. How do we go from there to here? And in this case, let's just write out the function is 1 over x minus 2 square. A is 2 and L is infinity. We don't really need infinity, but we just need to write at the end x minus 2, x minus 8 is less than delta. Right, we go from here to there. Right, so how do we do that? First of all, this square being positive and n being positive, we can write the fraction, right? Let's flip both sides. Flip both sides, we just have x minus 2 square, and then we have 1 over n. Now, what happens if we flip inequalities? Think about something very simple. 3 greater than 2, right? If we flip it 1/3 and 1/2, which one is smaller? Right? So if everything's positive, when we flip it, inequality will be flipped as well. Inequality will be reversed. So in that case, it's greater than, become less than. Now, this one is a square, this one have the absolute values. Remember, this works out perfectly. Absolute values, I mean, square root of a square is equal to absolute values of a. We talk about this in section 2.3. Yes. No. 2.5. Sorry. Right. So if we put a square root on both sides, and if we take the square root both sides, the inequality will stay the same. Right. 3 greater than 2. How about square root of 3 and square root of 2? Which one is greater? Square of 3 is 1.7 something. Square of 2 is 1.4 something. So inequality still stay. So take square root on both sides, when all of them are positive, which will remain the same. Inequality will stay the same. And square root of absolute values, we talked about that earlier. It is absolute values. and that. So in this case, we will say we will choose n to be, choose delta to be square root of 1 over n. Right, and the proof, we will write them in reverse. Right, proof. We'll need to have this for any positive n, for any n positive. Choose delta to be square root of 1 over n, so that if, now we write in reverse, if x minus 2 less than delta, then delta is said to be square root of 1 over n. Now we will write in reverse. We have this already. Now absolute values is square root of the square square both sides, and then we flip so the inequality will be reversed as well. Right. Now we have the function greater than n, which is that. So we can say the limit of this equal to infinity, because we can make it as big as we want to. So we can, that will go to infinity. All right. So in this section, we're not finding limits, proving the limit mathematically. So the proof usually will be in reverse of what we write. So either epsilon will be given, or in this case n will be given. We will find delta in terms of those epsilon or n. In that case, we write the proof in reverse, and that's pretty much it. So the conceptually, this is very important. But in theory and all, but in terms of finding limit, certainly we do not find limit by doing this. We're doing this to show that limit is indeed equal to some certain values. So this is the precise way to prove the limit of the function equal to something, not how do you find the limit of some certain function. All right. Anyway, I stop the section here, and see you in another video in Calculus 1. Thank you for watching.